Hello guys, welcome to my channel Civilizations. In this video, I will talk about the preliminary design of beam. I have already uploaded the video of preliminary design of slab. I request you to check that video too. I will put the link in the description. The main objective of preliminary design of beam is to find the preliminary size of the beam for further load calculations or simply to define the required beam size in ETABS or any other structural analysis program while modeling. Preliminary size of the beam gives you the depth and breadth of the beam. Before going on to the preliminary design of the beam, you need to know certain parameters of the beam cross-section. And the parameters are overall depth of the beam and effective depth of the beam. Here I have this cross-section of the beam. The result of preliminary size of the beam gives you this breadth of the beam and this depth of the beam. You can see here, these three circles represent the tension reinforcement. The reinforcement is always provided on the tension side of the beam. And this capital D represents the overall depth of the beam. Overall depth of the beam is the distance between upper edge and lower edge of the concrete section or beam section. Similarly, effective depth is the distance between upper edge and center of reinforcement of the section. The distance between the lower edge and center of reinforcement of the section is called effective cover. Preliminary design of beam is done by using two methods. One is deflection criteria method and another is moment criteria method. In deflection criteria method, it is all about span by depth ratios. We will have span from the architectural plan and we will also have the span by depth ratio from Indian Standard Code, that is IS 456-2000. From there we can calculate the required depth of the beam. And we will also have the thumb rule between depth and breadth relationship. So tentatively we can calculate the section size of the beam from deflection criteria method. The moment criteria method is all about finding the required depth of the beam such that it will be sufficient to resist the obtained moment in the given section. So what we do is we will calculate the depth from the deflection criteria method. Similarly, we will also calculate depth from the moment criteria method. And we will choose the maximum value in between them. And from the depth, we will calculate the breadth of the beam. Okay, this is the process for preliminary design of beam. You should follow these 1, 2, 3, 4, 5, and 6 process for the preliminary design of beam. The first is you should choose the critical beam for the design. That beam will be the critical beam which has the longest span and which takes the larger loads. To choose the critical beam, we need to see the architectural plan of the floor. Here is the architectural plan of the building. You can see here these are the columns and here are numbers of beam on this plan. So we are not going to design every beam, rather we should choose a critical beam for the design. And for the critical beam, we should consider two things. One is the span of the beam and another is the beam which takes the maximum load. So first go for the longest span of the beam. So here is the center to center distance between the grids, that is in between A and B, 12 feet 1 inch, 5 feet, 11 feet 8 inch, 12 feet 5 inch. Similarly on these directions you can see 14 feet 4 inch, similarly 8 feet 7 inch, and again this 14 feet 4 inch. So considering both the directions, I have 14 feet 4 inch which has the longest span. So 14 feet 4 inch here in between one grid and two grid, the distance is 14 feet 4 inch. Similarly in between 3 and 4 grids, the distance is 14 feet 4 inch. So for now, the beams which have a span length of 14 feet 4 inch, they are the critical beams. And one will be this beam. This beam has the span length of 14 feet 4 inch. Similarly this. So the beams represented by this circle represents the critical beam. Now we should consider another thing. The another thing is that that beam will be the critical beam which have the longest spans and which takes the maximum load. Slab loads are transferred to the edges or to the beams through inline theory. If you want to know more about the inline theory, I have already uploaded a video of one-way slab and two-way slab where I have described everything about load transfer of slab or inline theory load transfer to the edges. So please check that video too. I will put the link in the description. Red lines are the lines that are drawn at 45 degrees from every corner of the slab panel. So let's draw the 45-degree lines from every corner of these slab panels where our critical beams are lying. You can see here I have drawn a 45-degree line from every corner of the slab. So these two lines meet at this point, and similarly these two lines meet at this point. I connect these two meeting points by a line. This area of the slab load is transferred to this beam. This triangular area of the slab load is transferred to this beam. Similarly, this triangular area of the slab load is transferred to this beam, and this trapezoidal area of the slab load will be transferred to this beam. We need to do this to every slab panel. So let's do for all the slab panel here. And finally, this will look like this. You see here that end lines are drawn on every slab panel. This beam takes area, this trapezoidal area. This beam takes this triangular area. Similarly, here this beam takes this trapezoidal area plus this trapezoidal area from this slab. Again, all these beams in A, B, C, D, and E grids, I think this D grid beam, that is this beam, takes maximum area. Because as you can see here, this area is greater amongst all the areas drawn respective to that beam. So I think, or you can also check it from the by seeing the area, but by visualizing it directly, I can see that this area is greater amongst all these areas. So our critical beam is D12. That is, this beam will be our critical beam. So D12 is our critical beam. So we have chosen our critical beam for the design. One step is finished. Now let's design it by using the deflection criteria method. This is IS 456 2000 code, and we are on to the 37 page number, that is clause number 23.2.1. So again, I will remind you that we can have the span values of beam from architectural plan. So if we have span by depth ratios from this code, then we can calculate the depth. The basic values of span to effective depth ratios for spans up to 10 meter for slabs and beams will be, for cantilever structures it will be 7, for simply supported structures it will be 20, and for continuous structures it will be 26. But what we need is, we need limiting values of span to effective depth ratios. The limiting values of span to effective depth ratios are calculated by modifying these factors. And here are various modification factors: the modification factor for tension reinforcement, the modification factor for compression reinforcement, similarly reduction factor, and we will obtain the final limiting value of span to effective depth ratios. So if you need to know more about how these basic values is converted into the limiting values of span to effective depth ratios, you can refer to my previous videos of preliminary design of slab, which I will put the link in the description. Now we will have another easy method for calculating the limiting span to effective depth ratios for beams. So what we have is, we have final values of limiting value of span to depth ratios for beam through numbers of experiments and experience, and that is, the limiting value of span by effective depth ratio equals to 12 for simply supported beam and 15 for the continuous beam. I just showed you that the limiting basic values was say 20 for simply supported and 26 for the continuous, but I've already told you these values will go the modification as per these conditions written here, B, C, and D. But we have also the final value of limiting value of span to depth ratios through numbers of experiments and experiences used by the designer, and that is, limiting value of span by effective depth ratio equals to 12 for the simply supported beam and equals to 15 for the continuous beam. So this D12 is our critical beam, and its one end is discontinuous, that is it ends here, and another end is continuous, that is this beam will continually go to these directions. So it has one end continuous and another end discontinuous. Since the beam of our design is one end continuous and another end discontinuous, we use the average of these two values, that is 12 and 15. Limiting values of span to depth ratio for our critical beam will be 12 plus 15 divided by 2, that equals to 13.5. We have span length of beam equals to 14 feet 4 inch. We can see that from the AutoCAD. our critical beam is this D12, which has the span length of 14 feet and 4 inches. So span length equals to 14 feet 4 inches, which is equals to 4.368 meter, and we have span to depth ratio, that is 13.5. From this equation we can calculate the depth. So depth comes out to be 323.55 mm. This obtained depth 323.55 mm is the effective depth of the beam. So we should add half the reinforcement diameter and clear cover, that is effective cover, to the effective depth of the beam to obtain the overall depth of the beam. So 323.55 mm is the effective depth of beam, and overall depth of beam is, here I use 20 mm reinforcement steel. So overall depth equals to effective depth plus half the reinforcement dia, that is 10 mm, plus 20 is the clear cover, which equals to 353.55 mm. So let's take the overall depth of the beam is 360 mm. We have the thumb rule for the breadth of the beam, and breadth of the beam can be taken as 0.5 to 0.75 of D. So breadth of the beam equals to 0.5 to 0.75 of depth. I take the breadth of the beam to be 0.6 times the depth of the beam, which equals to 0.6 into 360 mm, and it comes out to be 216 mm. So let's take 220 mm breadth. So finally we have breadth equals to 220 mm and overall depth equals to 360 mm. So we have chosen the critical beam for the design, and we design it by using the deflection criteria method. We finished 1 and 2 steps. Now we are moving on to the third steps. Now we calculate the total load on the beam, and then we will calculate the maximum moment on the beam span, and then we will design the depth of the beam by using moment criteria method. So let's calculate the load on the beam. The loads taken by this beam will be dead loads of the slab enclosed by this area, live loads, surface finish loads of the slab, masonry load on the beam, and self weight of the beam itself. So the loads on the beam will be dead loads of the slab, live loads on the slab, surface finish loads, and masonry loads. So to calculate the dead load of the slab, we need to calculate the area enclosed by the yield lines. So to calculate the area enclosed by these yield lines, select this area and then see its properties. So here we have the area of 100.2 square feet. So we have this enclosed area 100.2 square feet. Now we are going to calculate the total load on the beam. You can see here, the enclosed area is 100.2 square feet, which equals to 9.31 square meter. And dead loads of slab equals to this area into, suppose the depth of slab is 125 mm or 0.125 meter. So area into depth equals to the volume of the slab into 25 kilonewton per meter cube is the unit weight of slab. So this will give the total dead load of the slab, which equals to 29.1 kilonewton. Similarly, live loads on the slab. Let's consider 3 kilonewton per meter square of live load is acting on that slab area, that is on that enclosed slab area. So we have the area of slab is 9.31 square meter, and into 3 kilonewton per meter square is the live load intensity. So that gives the 27.93 kilonewton live load on the beam that will be transferred to that beam. Similarly, consider the surface finish loads intensity of 1 kilonewton per meter square, and we have the area 9.31 square meter. If we multiply it with 1, then we will have the surface finish loads of 9.31 kilonewton. Ultimately, that load of slab also goes to the beam. And we have masonry over the beam, that is masonry wall over the beam. Let's consider the masonry wall of width 9 inches. Then we have the unit weight of masonry is 20 kilonewton per meter cube, and this 4.368 is the length of the beam over which the masonry is lying, and this 0.23 meter is the width of the masonry wall, and 3 is the height of the floor height. So it gives the total 60.3 kilonewton masonry load. These all loads are transferred to the beam. So total weight equals to 29.1 plus 27.39 plus 9.31 plus 60.3, which equals to 126.64 kilonewton. Okay, this is the total weight, but we need to calculate the weight per unit length. So weight per unit length will be total weight divided by length of the beam, which is 4.368 meter or 14 feet 4 inch beam. This will give 29 kilonewton per meter. For moment calculations, we need the factored weight. That is, to calculate the factored moment, we need factored weight, and factored weight here I take the factor 1.5 to calculate the factor weight, which gives 29 into 1.5, which is equals to 43.5 Newton per meter. Here we completed these three number tasks that we calculated the load on the beam. Now we are going to calculate the maximum moment on the span on the basis of size obtained from the deflection criteria method. Now we are going to calculate the maximum moment of the beam. Maximum moment occurs at the mid-span of the beam, and the value of maximum moment is given by the formula WL square by 8. So we have W 43.5 Newton per meter. We just calculated the factored weight per unit length, and length 4.368, that is the length of the beam, WL square by 8, and that gives the 103.7 kN meter, which is the maximum factored moment. So we finished the 4 number task, that is we calculated the maximum moment on the beam. Now we will move to the 5 number that we are going to design it by using moment criteria method. So now let's look what is the moment criteria method. So in moment criteria method, we have the formula for the bending moment of a section of beam. And that bending moment formula is given by this mu limit is the bending moment, that is maximum bending moment at a section, and that equals to q limit into bd square. The formula for the q limit is q limit equals to 0.36 times fck times xu limit divided by d into 1 minus 0.42 times xu limit divided by d. So this is the formula given in IS code, that is IS 456-2000 code, and you can find this formula in various textbook also. We have already calculated our moment, that is maximum moment at the span of the beam, and we are using the formula moment m equals to q limit times bd square. At first we need to calculate the q limit value, and q limit, for calculating the q limit value we need to know fck and xu limit by d. Fck is the maximum characteristic compressive strength of the concrete. If we use 30 MPa concrete, then Fck will be 30 Newton per mm square. Xu limit is the maximum distance of neutral axis from the upper edge of the section. The value of Xu limit by D depends upon the grade of steel used. If we use Fe415 steel, then the value of XUL by D will be 0.48. Now we can calculate the value of Q limit because we have FCK, we have XUL by D, and we can calculate Q limit equals to 0.36 times FCK times XUL by D for Fe415, that is 0.48, and 1 minus 0.42 times 0.48. This will give the value of Q limit to be 4.138. Since we have maximum moment of 103.744 kN that we have already calculated, that is 103.744 into 10 to the power 6 Newton mm. Now we can use this formula m equals to q limit times bd square. We have m 103.744 into 10 to the power 6 and q limit 4.138 into b times d square. Here I have used b as a 0.6 times depth of the beam as per the thumb rule. Now in these equations the only unknown quantity is the depth of the beam. From these equations we can calculate the depth of the beam. The obtained depth is 347 mm. Remember that this depth will be the effective depth of the beam. Now to calculate the overall depth of the beam, we need to add half the reinforcement diameter plus clear cover to the effective depth of the beam to get the overall depth. And if you add 347 plus 10 half the reinforcement diameter plus 20 clear cover, we will get overall depth of the beam to be 377 mm. We just use a higher value of it nearest to 0, that is nearest to 10. So here I add up the overall depth of 380 mm. Well, the overall depth of the beam calculated from the deflection criteria method was 360 mm, but from this moment criteria method, overall depth of the beam is 380 mm. Thus we choose the maximum value, and our final result of preliminary design will be the overall depth of the beam will be 380 mm and breadth of the beam will be 0.6 times 380, that equals to 228 mm. We will convert it into nearest 10, so that will be 230 mm. If the value obtained from this moment criteria method was less than that of the deflection criteria method, then we will use the final design of that deflection criteria method. But here in this case, we have the value greater than from that of deflection criteria method. So our final result of preliminary design of beam is the overall depth of the beam to be 380 mm and breadth of the beam to be 230 mm. So guys, this is all about the preliminary design of beam. If you like this video, please subscribe our channel and share with your friends. Thank you.